All right, this note is on reviewing some of the stuff on acids and bases, and then applying equilibrium ideas to the acid-base situations that we're going to encounter, particularly when we're dealing with weak acids and weak bases. All right, so let's review, first of all, our Bronsted-Lowry theory of acids and bases. Remember that an acid is a substance that can donate a proton, and a base is a substance that can accept a proton. With an acid, we have to have the hydrogen in the formula. And any negative ion can be the base, not just the hydroxide ion. Any substance can act as an acid only if another substance acts as a base. So with the Bronsted-Lowry theory, you've always got acids and bases working simultaneously, right? So if something donates a proton, something else has to accept that proton. It just doesn't go into oblivion, right? So if we have, let's say, the situation where we put hydrochloric acid into water, then water actually acts as the base in this scenario. And so we have the acid donating the proton going to the base, the water molecule, forming the hydronium ion, which is our conjugate acid to the water base. And then we have the chloride ion being left over after the hydrogen is gone, and that's our conjugate base to that acid. So we always have these conjugate acid-base pairs, right? So they're related by that transfer of a proton. So conjugate base is chloride, conjugate acid here is the hydronium ion. All right, so this is nothing new. We covered this last year in grade 11, so everybody should be familiar with that. Hopefully this is a reminder. Remember also with water, it has the, like normal neutral water has a pH of 7, and we consider that to be what we call neutral. Well, the pH is actually a measure of the concentration of the hydronium ion. And if that's the case, then water has to have some hydronium ion concentration, actually 10 to the minus 7, concentration, because that's the definition of what pH is. So how do we get that? Well, we have this autoionization of water property where water actually reacts with itself to form a hydronium ion and a hydroxide ion. And this equilibrium is always in play in any solution that contains water. So there's always going to be some hydrogen or hydronium ion concentration. And the reason for that is because just some water molecules happen to give up a hydrogen, goes to another water molecule to form the hydronium ion and leaving a hydroxide ion. Now these concentrations are usually very low, like 10 to the minus 7 is a fairly low concentration. And so this is why we have this idea of pure water having a pH of 7. Now, we can write our equilibrium constant expression for this, but because we have two liquid waters on the reactant side, they wouldn't appear in this. Their constant concentration is rolled into the constant value, the K, and we call this the Kw. So Kw is written as the hydronium ion concentration times the hydroxide ion concentration over the two concentrations of water, which are rolled into the K value because they're constant. So Kw then is equal to the hydronium ion times the hydroxide ion concentrations. So when water is at SATP and equilibrium is reached, the concentration of hydronium and the hydroxide ion is 1 times 10 to the minus 7 molar. All right. The Kw for that is 1 times 10 to the minus 14. Right, and so then we have the pH of that neutral solution is 7, because that's based on the negative log of the concentration of the hydronium ion. pOH would also be 7 because it's the concentration of the hydroxide ion concentration, or the negative log of the hydroxide ion concentration. So if something is acidic, the pH is less than 7, and basic solutions have a pH greater than 7. All right. Now, we also talked last year about strong acids and weak acids. Remember, strong acids dissociate 100% into ions in water. In other words, the total hydronium ion concentration is the same as the acid concentration. So 1 mole per liter of hydrochloric acid would give us 1 mole per liter of hydronium ion concentration. Okay, examples of strong acids. Here's the other ones. Sulfuric acid, nitric acid, chloride, bromide, and iodide ions will give you strong acids with hydrogen. Weak acids dissociate only slightly in water, usually about 1 to 10%. And in this particular case, with a weak acid, the hydronium ion concentration is going to be less than the acid concentration. And so hydrogen fluoride, for example, is a weak acid. When you react that with water, you get the hydronium ion and the fluoride ion, and it's an equilibrium situation. Other examples would include acetic acid. You're familiar with that one. Strong bases, same idea. It dissociates 100% into its ions in water. All oxides and hydroxides of alkaline metals, group 1, or alkaline earth metals below beryllium are strong bases. Sodium hydroxide, potassium hydroxide, barium hydroxide, examples of that. Weak bases, though, dissociate only very slightly in water. So ammonia, for example, is a weak base because we form this equilibrium where we have the formation of some ammonium ions and some hydroxide ions. All right, so let's do an example of how we would use this information. Okay, so calculate the hydrogen ion concentration and the hydroxide ion concentration in a 0.01 molar solution of HCl. Okay, well, this one's fairly easy. It's a strong acid, so therefore the hydrogen ion concentration is the same as the hydrochloric acid concentration, which in this case is the 1 times 10 to the minus 3 moles per liter. So using the our Kw equation equals hydroxide ion times hydrogen ion, rearranging to solve for the hydroxide ion concentration, we get 1 times 10 to the minus 14 over 0.001, and that gives us 1 times 10 to the minus 11 moles per liter. Another example, let's calculate the concentration of hydrogen ions in a 0.3 molar solution of barium hydroxide. Now, one of the things you'll notice in that last example, I talked about hydrogen ions, not hydronium ions. Okay, you will find that in the acid-base scenarios, we kind of flip between the Bronsted-Lowry and the Arrhenius definitions almost without thinking about it, because hydronium ions concentrations and hydrogen ion concentrations really are the same thing when we're talking about acids and bases. All right. So let's take a look at this particular example. Calculate the concentration of hydrogen ions in a 0.3 molar solution of barium hydroxide. So hydroxide ion concentration here, it's barium hydroxide, so it's a strong base. So the hydroxide ion concentration is going to be the same as the compound concentration. So to figure out the hydrogen ion concentration in this equilibrium, we're going to have the Kw divided by the hydroxide ion concentration, and in this case that's going to be 3.3 repeated times 10 to the minus 14 molar. All right, so the pH scale measures the concentration of the hydronium ion, and it's based on that negative log of the concentration of the hydronium ion or hydroxide ion, so for the POH scale. This is just kind of an outline of the logarithms and how they work. You should remember that from your senior math. If you haven't taken the senior math course, logarithmic scale is a type of kind of an inverse of an exponential scale, using 10 as the base. So 10 to the x would be the inverse function of the log. And we use this particular scale to determine our pH, so that the pH is equal to the negative log of the concentration of the hydronium ion, or hydrogen ion, because we, as I said, depending on which definition you're using, we can use either H plus or H3O plus. All right, so the hydrochloric acid is 0.01 molar. What's the pH? Well, we calculate the pH based on the concentration of hydronium ion. For a strong acid like hydrochloric acid, the hydronium ion concentration is the same. And so the negative log of 0.01 works out to 2. The H plus, the hydrogen ion concentration for a solution with a pH of 2.5, so that's 10 to the minus pH, would work out to 0.003162277. All right. Sig-dig rules are different here. The number of decimal places in the logarithm are equal to the number of significant figures in the concentration. Okay, so we look at 2 decimal places here in the log, and so we use 2 decimal places, 2 significant digits in the pH value. Okay, all right. POH is similar to pH, except that it's a measure of the concentration of hydroxide ions. Same idea applies, but if you'll notice from the Kw expression, for neutral water, the Kw was equal to 1 times 10 to the minus 14, right? And this is where we get at SATP the relationship that POH is equal to, or sorry, POH plus pH is equal to 14. So that gives us kind of a loop of calculations that we can do. Here's an example where we're looking at pH, POH, and concentration of hydroxide ions of an acid solution. Now, this is a strong acid, so the molar concentration of the acid is the same as the hydronium ion concentration, or hydrogen ion concentration. And so the pH is easy to figure out. Negative log of this concentration is equal to 1.366531544. Okay, POH is equal to 14 minus this value, which is going to be 12.63346.846. The concentration of the hydroxide ion is 10 to the minus POH, which is going to be 2.3 times 10 to the minus 13. All right. For an equilibrium acid dissociation reaction, the Ka value is equal to the concentration of the 2 ions, the IH plus ion and whatever anion is there, over the concentration of the acid. This is what we call the acid dissociation constant. All right. For strong acids, we just say it's a very large number, because essentially you're taking the concentrations and essentially dividing them by 0, which doesn't work, right? Because in a strong acid, this concentration is 0 because all of the ions have gone to, all of the acid is dissociated into its ions. So with this being a 0, that gets you an infinitely large number. So we just say that the value is very large for strong acids. For an equilibrium base, dissociation reaction. It looks like this. The Kb value, or the equilibrium base constant, looks like this. And again, for very large, or for very strong bases, we have a very large Kb value. Let's do an example. A student prepared a solution of 0.01 molar can never say this, propanoic acid, and found the pH to be 2.96. What's the acid dissociation constant for propanoic acid, and what is its percent dissociation? Okay, so to figure this out, we first of all set up our equilibrium constant expression. So acetic acid, in this case propanoic acid, with water gives us the propanoate ion, and the hydronium ion. All right, let's set up an ice table. So we get a 0.10 molar concentration of the acid, 0 of the ions. The change to reach equilibrium, this has to come down by some value x. These go up by some value x. And the equilibrium x values will be 0.1 minus x, x, and x. All right, so for hydronium ion, the 10 to the minus pH is going to give us 10 to the negative 2.96. And so that value is going to be 1.1 times 10 to the minus 3 molar. We put that into our Ka expression, we get this. All right, so we know that our x value then is going to be our 1.1 times 10 to the minus 3. All right, so that value gets squared because it's the two multiplied against each other. The 0.1 minus x is our acid concentration. And when you plug in the numbers and do the math, you get 1.2 times 10 to the minus 5 as our Ka value. All right, now from this, we should be able to figure out, okay, what's going on here in terms of the percent ionization, or dissociation, I guess. So what we do is we take our acid dissociated concentration over our initial concentration, and we multiply by 100%. So the 1.1 times 10 to the minus 3 molar over the 0.1 molar times 100% gives us 1.1% dissociation. Let's do another example. Okay, so this is a 0.05 molar solution of nitrous acid. Has a Ka value of 5.6 times 10 to the minus 4. What's the pH of the acid solution? All right, so nitrous acid is HNO2. In water, we get NO2 minus and hydronium ion. Again, set up an ice table. The initial concentration is 0.050 molar. Minus, it'll come down by x value. The NO2 and H3O plus will go up by x, leaving us with 0.05 minus x, x and x. So the Ka value then is 5.6 times 10 to the minus 4, which is going to give us x squared over 0.05 minus x. Set up the quadratic equation. Solve for x. We get two values, negative 5.8 times 10 to the minus 3 or 5.02 times 10 to the minus 3. We can't have a negative value here, so that one is no good. So the 5.02 times 10 to the minus 3 is the concentration of the hydronium ion. So from that, we can then figure out the pH is the negative log of that, which works out to 2.3. All right, so there's homework questions for this. Try those and we can talk about them in class.